Okay. I think we are ready to go. So good evening, everyone, and welcome. Today we are exploring a fascinating topic that connects psychology, cognitive science, and quantum theory, known as quantum cognition. Quantum cognition is an interdisciplinary field that um, uses mathematical frameworks of quantum theory to model and explain different aspects of cognitive processes, such as decision making, memory, and processing. It will be a great pleasure to learn more about this from Emmanuel, who has been at the forefront of this research. Very briefly, Emmanuel studied physics at Imperial College. He did his PhD in experimental psychology at the University of Oxford, and since then he's been an active researcher for nearly 30 years. He's currently a professor at the Department of Psychology at City University London. Emmanuel, welcome to our event. We are delighted to have you here today to discuss this fascinating topic.
Salma, thanks very much for the invitation and welcome everyone. So it's the purpose here tonight is to give you less so what quantum cognition is, but more so to try to illustrate the motivation for using quantum in psychology, in behavioral sciences. So there's going to be very little mathematics. There's going to be quite a lot of the sort of empirical background that led to this research program. I've got the chat open, so if you have any questions, please just raise them. It's an introduction which is as little mathematical as possible. But still, if you have any questions as we go along, please just put it on the chat, and I'll try to say it. And also welcome to some of my colleagues that I saw joining, like Pavel Blazak and Aram Huang and RFS. So apologies if you heard some of this in the past. I'll try to offer some original bits. So the title is Why Quantum? That is why sometimes we as in cognitive psychologists, experimental psychologists, use quantum theory in psychological theory in cognition. And okay, I'll start with a really famous result, which is almost, I mean, so surprising, it's almost entertaining. So this is, from those of you who've not done psychology, I'll be assuming a little bit of familiarity with basic behavioral tools. But again, if anything is kind of a little too unfamiliar, please put it in the chat or interrupt me. So anyway, so this is a questionnaire, right? It's a Gallup poll. So Gallup poll, as you know, it's kind of a series of questions, and Gallup polls are used quite often in to gauge public opinion about all sorts of issues. So Gallup polls are quite important. On voters on the hedge might use the results from a Gallup poll as a way to guide their own behavior. These things are instruments with some consequence. So this is a study using an actual Gallup poll with a large sample, about 1,000 participants. And participants were asked in this order: is Clinton honest and is Gore honest? Now, the two questions were just one after the other. They were not related in any way. And with this particular order asked, the proportion of yes responses to the Clinton question was about 50%, and to the Gore question, 68%. And that's unsurprising because we know what Clinton did, we know who Gore was, etc. Interestingly, if you reverse the question order and you ask the Gore question first, the percentage yes to the Gore question rises to 60%, and to Clinton, sorry, drops to 60%, and to Clinton rises to 57%. And that's like a massive difference. If you're Bill Clinton, you want the question about your honesty to be asked after the Gore question. And in fact, such kind of order effects are well known in the experts who develop these Gallup polls. And question order can be employed as a way to manipulate the answers that people get. This is a sort of more empirical paradigm, but still quite interesting. So it's called a categorization decision-making paradigm. And participants were presented with faces, and the faces were piloted to look similar in all sorts of ways. And so participants will always ask a question about whether to attack or withdraw. So imagine you're looking at the face, and depending on your impression of the face, you make a decision. Shall I attack or shall I withdraw? Now, sometimes participants would be asked prior to this decision question whether the face were a good or a bad face, right? And you can see what the logic is. If you categorize a face as a good one, perhaps you withdraw, you don't attack, and vice versa. Now, the results were the probability of attack, right? And this is the law of total probability, which is a very, very basic principle in classical probability theory. The probability to attack without any information about whether the face was categorized to be good or bad should be just the sum of the probability to attack and a good categorization, and the probability to attack and a bad categorization, right? Well, it wasn't like that at all. When the probability, so I mean, there are three numbers here, and actually the result is quite funny. So look at this number here, first of all, 52%, right? So when participants saw a face they categorized as bad, 52% of them decided to attack. So, imagine you're sitting in the living room, you see out in the garden somebody, he looks bad, about half of you would decide to attack, which is sort of fair enough. I mean, it's quite interesting that when participants categorize the face as good, still 7% of them decided to attack as well. So, you see some kind of, old lady in your garden or some child who got lost, you still decide to attack because why not? The funny thing is, for participants who did not make this categorization question, 69% of them decide to attack, which I call this the shoot first and ask questions later finding. So this is a sort of, again, this is a result that challenges expectation from what we consider rational. So I'll talk about this shortly, because obviously one is talking about a finding which is classified as a bias or something erroneous in some way. Well, the question is, so what is the rational or what is the unbiased way to behave? Okay, so we've got, right. So we've got, I'm going to talk about the conjunction fallacy, and some of my colleagues here in the talk, like Adam, would have heard this like literally a million times. But if you're unfamiliar with decision psychology and cognitive psychology, this is possibly the most famous empirical finding in all of the decision empirical literature. So this concerns an experiment that was run, nearly 30 years ago. So, apologies for the massively out of date stereotypes for feminists. Participants were given a short vignette. Participants were told of a hypothetical person called Linda, who was described as deeply concerned with issues of discrimination and social justice, and participated in anti-nuclear demonstrations. And then participants had to rank order various possibilities about Linda. Now, the key ones was that Linda was a bank teller, right? And Linda was a bank teller and active in the feminist movement. Now, most participants would choose the first option. Most participants would choose the second option as more likely than the first one. And that's the famous conjunction fallacy. The conjunction fallacy, so I'll show you shortly why the conjunction fallacy is such a problem. But basically, this is a judgment along the lines of saying that, well, I think it's more likely that it will rain in London that it will rain and snow in London in December than just rain, right? So you can see why this is a paradox, right? You consider December, right? You consider all Decembers in the past. You look at all the days in which it would rain in December in a particular city. then from these days, a subset would be the range on which the days on which it both rains and snows. And this finding here is telling us that participants find more intuitive the converse. They find more intuitive the more restrictive possibility compared to the less restrictive one. Okay, so let's see how this would work in sort of more schematically. So classical probability theory works as sample spaces. We'd have like a sample, we'd have a big set of all possible lindas, and a subset of these possible lindas would be consistent with a feminist property. And then another subset would be consistent with a Bank-Teller property. Now, the point is that the intersection, right, the lindas which are both feminist and Bank-Teller can never be more numerous than either the Bank-Tellers or the feminists. The conjunction fallacy is a huge fallacy. And what's important about it, it's not just that we catch out naive observers, participants, in making a mistake, but rather that even after participants see this explanation, they still somehow feel that the statement that Lynn's a bank teller and a feminist is more likely than just being a bank teller. So we've got like there's a clash, and it's like these big clashes that drive new theories. There's a clash between sort of formal theories telling us, at least formal theory of this type, and human intuition. And there's been this finding, this conjunction fallacy, has been the incentive for an enormous amount of theory. Okay, I'll just kind of offer you one more fallacy example just to bring the point home. So you might argue that in the case of whether Linda is a bank teller and a feminist, well, this set theoretic structure is not as transparent, and that kind of like makes it easier for participants to fall foul of the fallacy. However, this is a version of the conjunction fallacy that I personally like very much. And participants were given the statement: it is a common in the Scandinavian peninsula to come across people with both blue hair, sorry, I keep meaning to correct this, with both blonde hair and blue eyes. Imagine such a person chosen at random and choose the most probable between the following three statements. The individual has blonde hair and blue eyes, and blonde hair does not have blue eyes. Now, if you basically imagine a whole bunch of like Scandinavian dudes, right, side by side, clearly you can't have more people who both have blonde hair and blue eyes, right? This second statement, well, surely you just enumerate all the people with blonde hair, and from these, you select a subset with blue eyes, and that's a probability. And yet somehow, again, there's a clash. There's a very strong clash between the logical structure of the problem and what intuition is telling us. It's like we have a little person inside our minds jumping up and down, saying, well, of course it's more likely to have both blonde hair and blue eyes. And Scandinavian people are like that. But logically, that's not correct. Okay, so there are tons of problems like this. There are conjunction fallacies. So I put another order effect here. That's kind of notable because it's a finding that was done with actual medical practitioners. So the probability of an infection was rated to be different if particular information was given in one order versus another order. And that's shocking, of course, because imagine going to the doctor and worrying about whether if you present your symptoms one way versus another, you get different answers. Okay, so taking a step back, we've got all these results which I've told you they're fallacies, but I've not said very much about the way in which they're fallacies. And we sort of like, we'd like to take a step back and try to understand, what's common in these, between all these different findings, or whether maybe there's nothing common, right? Maybe they all just the mind does different things in different cases. But also, I'd like to try to well, decision theorists have tried to sort of understand that this type of results in terms of like two very, very important distinctions. And I'll talk a little bit about these two distinctions. And then hopefully this will lead us naturally to how quantum theory can help explain these distinctions. So two distinctions that have been really crucial in the development of decision theory is the rational versus heuristic decision making. And we'll talk shortly about what these things are. And also the system one versus system two. If you've gone literally within 100 miles of behavioral economics, you'll know what this is. If not, I'll explain it shortly. Okay, so let's talk a little bit about how people should reason. And the unquestionable standard for rational behavior is a classical probability theory, Bayesian probability theory. If you've done maths or physics, you probably know what this is. It's basically the standard probability theory. And there are many results that justify this assertion. I don't think there's any decision theorists currently who would disagree with the statement that if we could, the rational way to do probabilistic inference is basically Bayesian theory. And of course, Bayesian theory in some ways, it's founded on axioms that are extremely logical. For example, probability of A and B is the same as probability of B and A, right? I mean, that's very, very logical. Nonetheless, we also have all these fallacies, like the conjunction fallacy, or this illustrates the disjunction fallacy, which is not terribly important for now, but it's in the same category of findings as we discussed. Okay, so we've got there are some formal results that show Bayesian theory to be the rational standard for human decision making. So let's take this. Let's keep this thought. Now let's take another step back and look at what animals are doing. Now, of course, an animal, any animal has to carry out tacitly in some form, obviously, a law of probabilistic inference. For example, about predation risks, mating, foraging. These are all essentially problems of how to encode statistical structure in the world. And there is a body of work that shows that as far as we know, as you can imagine, it's not straightforward to make studies into animal cognition of this sort. But the evidence that exists seems to indicate that animals tend to be Bayesian. That is, if you're a squirrel and you're adjusting your behavior in relation to predation risks, you update your probabilities in a way which is consistent with Bayesian theory. So that's thought number two. Thought number one is there are some formal results indicating that the rational way to carry out probabilistic inference is Bayesian theory. We look at animals, right, who, as far as we know, well, it looks at least, they have less developed minds than we do, and they're also Bayesian. So why can't we be Bayesian as well? Why does it look like there are so many cases where humans produce behavior which is inconsistent with the axioms of Bayesian probability theory? And that, in a nutshell, is the answer. The problem is that at least one major problem is that the range of questions an animal has to deal with is much, much smaller than the range of questions a human has to deal. And the problem with baseline Bayesian theory is closure. If you basically have a set of questions, let's for example say we've got a series of questions Q1, Q2, Q3, which could be anything. Could be about Linda in our earlier example, whether Linda is a bank teller or a feminist, or she has black shoes, or she's got a nice house, or whatever. So we've got a set of questions. Then Bayesian theory requires that we can always construct a joint probability distribution for all these questions. In fact, that extends to all the questions that we can possibly imagine. And that quickly becomes basically intractable. That is, it's not possible to keep constructing these more extensive probability distributions. That is, put differently, for any set of questions, Bayesian theory requires you to be able to have an answer for any combination of outcomes. And we don't do that. Humans don't do that. Humans, our minds quickly sort of, for lack of a better phrase, run out of capacity when it comes to being able to consider a lot of questions concurrently. Okay, so I've got an example here. I'll just very quickly show you the extent of the problem. So, if you're from the UK, you know about Brexit, right? I mean, it's almost old news now, but still, it was a very, very big debate when it happened. And of course, Brexit is not a single question, right? Brexit is a combination of several questions in relation to the economy, labor laws, etc. So let's say we got the Brexit question and like 9 questions related to Brexit, such as about whether it's going to be good for the economy, labor, etc. Now, if we keep, just give me a sec, it's misbehaving a bit. If we keep, right, if we keep a joint probability distribution means that we need to be able to resolve to have a probability for all possible combinations of yes/no outcomes for our Brexit questions. If we have binary questions, that's basically, hold on, there. If we have 10 binary questions, that's 1,000 probabilities. If we add one more binary question, we get 2,000. 5 more, 100,000. So you can see that as we increase the number of questions that we have to consider concurrently, the number of possible information we have to somehow resolve just becomes really bigger and bigger and bigger, exponentially so. So basically, baseline Bayesian theory is intractably complex, given the multitude of questions humans have. And that's not a new insight. That's been known since the 1950s. And resolving this question has been the biggest problem, the biggest challenge in psychological theory. I'm not just talking about decision making. Across all of psychology, arguably, this is the most important question: how to resolve the challenge between the intractability of baseline Bayesian inference and what humans are doing. And basically, this question has been associated with the only 3 Nobel Prizes in psychology: for Herbert Simon for the idea of bounded rationality, Daniel Kahneman for, well, prospect theory and heuristics and biases, and Richard Thaler for nudges. I mean, you might think that there is a Nobel Prize to Jeff Hinton for neural networks is related as well, but anyway, that's arguable. Also, the Ramachal Prize, which is the biggest prize in cognitive psychology, was given recently to some researchers who've been working on exactly this question. So what does the mind do, right? How does the mind resolve this problem of trying to squeeze in the impossibly complex Bayesian inference into a system with finite resources? Okay, so I mean, to be sure, there is some evidence that sometimes cognition is Bayesian. That is, if you look at like specific cases for specific individuals, people look Bayesian, but of course not always. So how do we characterize the cases when behavior is not Bayesian? And there are there've been a couple of proposals. Standalone heuristic principles has been a super popular approach. That's the Kahneman, Tversky, Thaler tradition. We see a behavior like the conjunction fallacy. We try to come up with a heuristic that describes this behavior. But also the Bayesian researchers have tried to come up with variants of Bayesian theory, which are more bounded rational. That is, they are as Bayesian as possible, but expressed within a system of finite resources. Okay, so let's talk about system 1. So we've talked about distinction 1, rational versus heuristic reasoning, and we've tried to frame it a little bit as a clash between what's ideal, Bayesian inference, which is rational, and what's possible, which is heuristic inference. Let's talk a little bit about system 1 versus system 2. So system 1 versus system 2 is a distinction that's been kind of discussed for a while in psychological theory, but it was popularized by Kahneman. System 1 is meant to be rushed, reflexive, intuitive, automatic, fast. System 2 is meant to be thoughtful, analytic, considered, reflective. So the system one versus system two distinction is extremely popular in behavioral economics. So even major banks, they would have like Barclays, for example, they actually have an advisory facility for their investors, essentially explaining the system one, system two distinction. And I mean, they're not saying to people do one or the other. They're just telling them, well, just be aware there are these two different types of reasoning, and these are different characteristics. And if you're thinking of your investment decisions, you say, for example, if you're system one, you might fall foul to biases, things of that sort. So there is an inference here. There's a tempting inference. That was Kahneman's approach. That system one is heuristic. System two is is rational. Not Bayesian probabilistic reasoning is meant to be about intuition, not analytic calculation. But maybe the equivalence of system two and rational has not to do with calculation as such, but more about how much time you've spent considering a problem. Okay, so let me just tell you about how the Bayesians try to address this issue of these probabilistic fallacies, and then hopefully this will lead us to quantum, right? So I'm kind of like nearly half an hour in. I've not said anything about quantum, but like I said, my main goal is to show you why it makes sense to use quantum theory in this context, less so to explain the application of quantum theory. Okay, so what do the Bayesian researchers are doing? Well, one very popular approach is that the mind approximates Bayesian probabilities through sampling, but the sampling can be more limited, can be limited. So because the sampling is limited or heavily biased in some way, errors arise, or the sampling may have intrinsic errors, and these errors lead to fallacies. One could sort of adopt Bayesian networks. Bayesian networks are an incredibly important framework in causal inference. The With Bayesian networks, the idea is that you sort of like you identify you extend the dependence of questions in a particular way. You'd say, well, I've got some questions which are very dependent with each other on each other, and some questions which are not. And across this kind of like pockets of dependence, there's no need essentially to have like a joint probability inference. There's the idea of locally Bayesian inference that's associated with Fernbach and Sloman. Steve Sloman is a major cognitive psychologist. They introduced the idea of local computations. That is, when people reason in a causal case, they do so locally. They only consider a couple of considerations together. They don't consider all relevant considerations together. So hopefully you're getting the point that some part of like the debate for how to deal with fallacies has to do with Bayesian inference, but which is somehow limited, right? But also that perhaps part of the answer is that somehow the way the mind deals with probabilities is local. It doesn't look at all the range of questions we have, but it's looking at subset of questions and just kind of like focuses on these subsets one at a time, even at the expense of making errors. Now, quantum theory, well, that's exactly what it does. In a sense, quantum theory is basically computation which is local. So within each kind of these local pockets, it's perfectly Bayesian, perfectly rational in the traditional sense. But if you go from one pocket to the other, sort of fallacies or inconsistencies arise. So in quantum theory, we have like two types of questions: compatible questions, which for our practical purposes, that's not entirely true, but for our practical purposes now, they're mostly indistinguishable from Bayesian ones, and incompatible ones, such that resolving one question creates uncertainty for others. So quantum theory basically can be seen as a local version of Bayesian theory. in logical terms, the logical underpinnings of Bayesian theory is a Boolean algebra. The logical underpinnings of quantum theory is what's called the partial Boolean algebra, which means pretty much what you can guess it means, right? It's like Boolean algebra is kind of stuck together so that overall they're not consistent with each other. But like if you look at each one of these parts individually, as far as you know, it's like you're in a Bayesian universe. Okay, so right. So if you're going to remember only two things from this presentation, it's going to be basically this slide and the next one. Because in my mind, this explains exactly how uh, quantum theory helps address this issue of intractability of baseline Bayesian inference in thought. All right, so if we've got a Boolean algebra, then, like I told you earlier, you need to look at all your questions together. You need to you look at your questions and you need to be able to resolve any combination of these questions concurrently. There are no shortcuts. So let's go back to the Brexit debate. Let's say you got a whole bunch of finance-related questions, a whole bunch of immigration-related questions, etc. You need to be able to resolve any combination of finance, immigration, whatever questions together. The partial Boolean algebra, which is what quantum theory is, you can have a pockets of questions where things such that within each pocket things are Bayesian. So like let's say you're familiar with a whole bunch of finance questions together. So if you're having a debate on Brexit and finance, it's just like you're Bayesian, right? No fallacies, perfectly Bayesian rational inference. And the same like for immigration questions. But because you don't consider finance and immigration questions frequently together, when you try to consider some questions from finance and some questions from immigration together, then, well, these non-classical effects arise. Now, this separation can be accomplished in Bayesian terms as well. It just, as it happens, quantum theory has some very, very elegant and neat tools to relate this space to that space. And we've made some complex calculations. Essentially, there is a formal argument that the complexity of this is lower than the complexity of that. But of course, that comes at a price. It comes at the price of these inconsistencies as you go from one of these pockets to another. Okay, so that's the second slide to remember. So distinction one, Bayesian versus heuristic. Well, maybe this is about some questions being incompatible versus compatible, right? When questions are compatible, we're in a Bayesian sort of universe or a frame of mind. When questions are incompatible, well, we've got like this heuristic reasoning. System one versus system two. Maybe compatible representations require more effort to build. So maybe being more careless or rushed means that insufficient effort to build compatible representations. So actually recently with some good colleagues, Adam Huang and Zoe Ebelt, and of course, Jerome Bosmeyer, we've had quite a lot of evidence that as you are sort of more system one versus more system two, the pattern of fallacies changes the way we would expect across a whole range of fallacies. I've not talked about familiarity versus unfamiliarity, just to simplify things. But let's focus on these diagrams for now. So this diagram took ages to put together, right? But for me, it's like the most important diagram in the entire presentation because it just shows how quantum representations are a little bit simpler, but also you miss out a little bit on things. So they sort of try to capture this idea that when you're more rushed, less familiar with questions, maybe you start out being quantum. But like if you take the time to consider questions together, maybe you're more Bayesian. So that's kind of like a Bayesian space, right? It's a tensor product space between three questions. A question of whether a person is happy or not, healthy or unhealthy, or fit or unfit. Now, so you have like three binary questions. That would be an 8-dimensional space. So I'm only showing here 3 dimensions. So you can have like a dimension corresponding to whether a person is happy, healthy, and fit. A person who's who's unhealthy and unfit, but he's quite happy, right? And so on and so forth. So that's kind of like the Bayesian sort of space, if you want. It's an 8-dimensional space where you have one axis for each combination of questions. In a quantum space, if we've got a little bit of time to just give you a taster of how these quantum models are constructed, well, you've got an axis corresponding to happy, you've got an axis corresponding to healthy, and one corresponding to fit, and the angle between these different axes corresponds to how similar these concepts are. So I put like healthy close to happy and close to fit. I put happy and fit a little bit further away from each other. But the point is, if you imagine that, uh, in this space, right? How can I draw it right? In this, a line corresponds to different persons. Well, I can have a line being along the fit person, along the fit sort of like axis, showing that we basically have like a person who's very fit. I can show you a line which is kind of in between health and fit, showing somebody who's a little healthy and a little fit, but neither really, perfectly one or the other. But I can't have a line that overlaps with both happy and healthy. That's a quantum space. It's like if you know about quantum theory, you perhaps have heard of uncertainty relations. Well, the exact meaning of uncertainty relations is a bit controversial, but one expression of the uncertainty relations is that perfect certainty for like one possibility, like being healthy, means some uncertainty for the others. So there we are. You can be Bayesian, but it just takes more effort. It takes more dimensions, right? We think it takes more familiarity, more effort. A different type of people. Some people are more thoughtful and slow in their thinking, more systematic. Other people are more intuitive, more spontaneous. Or you can be, a little bit quicker, a little bit more intuitive, a little bit more reflexive. But this comes at the cost of not really knowing whether somebody can be both healthy and fit. You have like these uncertainty relations, and actually these type of representations lead to these order effects or these conjunction fallacies. Okay, so right, for some reason, just give me a sec. Okay, so I'm just going to show you some faces and just showcase some results. So quantum-like effects tend to be reduced with practice. Quantum-like effects tend to go together with order effects and conjunction fallacies. So that shows that it's not like individual heuristics, but like the same principle, the same approach, quantum theory, explains lots of things together. That's one of the major ways in which the quantum approach to these heuristics and biases has added value. And in general, it's possible to employ the same quantum model for several related findings. So John Bussmaker in this early work first showed that for a whole range of fallacies. And we've got a lot of new predictions as well. And there are many individuals who've been working on that. There's the QQ equality, a really important finding that Jerome and Rich and Joyce discovered. We've got the quantum Zinn effect. We've got violations of binary complementarity that requires some slight extension to the basic quantum approach that Adam Huang discovered. So there's been quite a lot of work. It's obviously it's meant to be an introduction, and like I said, my focus has been on trying to explain the motivation for trying to show how quantum theory found its way into psychology. Because it may seem like a strange proposition. Why? What does quantum? I mean, quantum theory is something from physics, right? What does that have to do with psychology? But it's basically this idea of that. What psychologists have found really appealing is this idea that you can have like these local spaces that between themselves are show these inconsistencies. It's like this basic idea from the probability part of quantum theory that's been relevant. Okay, so I've got 5 minutes, right? Or something like that. Selma? 5 minutes. Okay, so let me try to. I'm not going to sort of do that, but let me try to illustrate so the sort of the very basic approach for how to construct a model for the conjunction fallacy. I mean, if you've done quantum theory before, that's going to look trivial. If you've never come across quantum theory, it may be a little bit of a mouthful, but I'll try to make it as simple as possible. So probability information is represented in a big vector space with some convergence properties called Hilbert space. A vector in that space called the state vector represents a system. And in our case, the system is the mind of a person in decision-making situation. So for example, for the conjunction fallacy, the state vector is the mental state of a participant after reading the Linda story. Each question outcome in a classical space is a subset of the sample space. For example, a question outcome like rolling a die will reveal a 6 is a subset of all possible outcomes after rolling a die. So that's a classical space, right? In a quantum space, each question outcome is a subspace. It's basically in a two-dimensional diagram, these subspaces will look like axes. They're raised. They're not basically axes because they haven't got directionality. But I'll show you shortly an example how this looks. But just take it. Outcomes are like individual sort of lines in that space. And the basic idea, the basic operation we need is that of a projection. So we take a vector and we project it onto a subspace. So for example, let's say this is the mental state of a participant. And let's say this plane here, this is a two-dimensional space, corresponds to possibility A. Then the projection of psi onto A is this blue line here. You just literally slam it down. And a famous theorem in quantum theory says that the probability is the squared magnitude of the projection. In fact, there's a famous theorem showing that if you want to associate subspaces with probabilities, the quantum way of doing it is the only way of doing it. And that's a remarkable result. Right, in classical theory, so let's keep that. And let's keep that as well. And let's go here to an example for the conjunction fallacy, right? So literally in 2 minutes, we'll build a very basic model for the conjunction fallacy using quantum theory. So we have like two axes for bank teller and not bank teller. Remember, they're perpendicular to each other. Remember, probability is projection. So if you project onto here, if the probability for not bank teller is 1, you want 0 probability for bank teller. The state vector corresponds to the impression a participant would have about Linda after reading the story. And let's keep that. Let's explain the idea of projection. If I'm interested in the probability that Linda is a bank teller, I take my mental state and I project on bank teller on the bank teller array, and then I square this length. And that squared length is the probability that a participant who has just read the Linda story thinks that Linda is a bank teller, right? I mean, again, just ignoring the algebra, hopefully the main idea that these are my question outcomes, this is my mental state, this is a sort of measure of probability. Hopefully that's intuitive enough. Now, let's introduce the question outcomes for the feminist question. Now, how you place them? Well, that's a good question. But for now, just observe that I've put them in such a way that actually the probability that a participant thinks Linda is a feminist is quite high. Because look, if I project onto the feminist ray, I've got a large projection. So, I mean, that seems to square well with the assumptions we made about the problem about Linda. So I've got my question outcomes for feminism, and now I kind of need to think of how I'm going to do conjunction. Now, for conjunction, I can't evaluate both a bank teller and feminist question outcomes together. In order to do that, I would have needed a single axis with both question outcomes, and I would need a 4-dimensional space, tensor product of the two questions, right? So the only thing I can do, the best thing I can do rather, is to compute a sequential projection. And actually, that kind of makes sense in various ways because if you look at this quantity, the probability of sort of a sequential projection will that decomposes into a product of the marginal and the conditional as you would want. But let's leave that. Literally, the last minute I've got, observe that if I do this sequential projection from feminist, from the initial mental state to feminist and then to bank teller, then I get a longer projection than if I have a straight projection to the bank teller subspace. Now, this is really a crash introduction to quantum theory if you've not come across it. And if you know about quantum theory, you probably have all sorts of questions. But the main thing to illustrate is that actually this very simple diagram, this very simple representation, allows a situation whereby the conjunction, or at least a sequential conjunction, is higher than the marginal. So at the very least, hopefully this shows that the conjunction fallacy is allowed with this scheme. Now, the circumstance under which you get a conjunction fallacy or not, and how to build a model of out of this, well, that's a different story. But at the very least, you have a situation where, well, something that looks paradoxical from one probability theory, Bayesian theory, actually is possible within quantum theory. Now, there are lots of qualifications. I'm running out of time, so I'll just be super brief. Qualification number one is that's not a psychological model. That's just a calculation that shows conjunction fallacy is possible. To do a psychological model, you need lots of additional things. For example, some assumptions as to when things are compatible and when are not. You need a response mechanism, and that was Adam Huang's contribution to incorporate all that within a sequential sampling response mechanism. You need other considerations. You need to understand, well, so what am I having like one probability theory that tells me a result is correct and another that's wrong? I mean, how does that square with the rationality? So this kind of like a longer set of questions. But at the very least, please just see this result and think, well, what was irrational with Bayesian theory, at least it's possible in quantum theory. And that gives us hope that quantum theory is a good framework for these fallacies. The main strength of quantum theory, again, is not that it can do a calculation like this. It's just that a model based on the principles that allow you to model the conjunction fallacy can model a whole range of other fallacies as well. So let me have like one final slide, which shows Peter and Jerome, who basically initiated this research program. Their book, it's got a second edition recently. It's still basically the best book for how quantum theory is used in cognitive psychology. So I'll stop there. Thank you for your attention, and apologies if it was a little bit quick at certain points.
Amazing. Thank you for that fascinating talk, Emmanuel. Obviously, studying the human mind demands innovative tools and methodologies. And I'm particularly amazed by how principles of quantum theory can be applied to model non-classical patterns of human thinking. So this talks raises several interesting questions, I can imagine. So let's open the floor to discussion. We would love to hear your questions and comments. Please use the raise hand button to ask them yourself or type them into the chat box that we can read and answer. Maybe I can ask the first question actually while I was listening your talk. This came to my mind. Emmanuel, how might these models can inform educational tools? Do you think that in the long term, but I know no educationalists are working on this, but do you think that there might be some impact on education or education tools or some methodologies in the near or far future?
So, I mean, the mind. I mean, the main premise in a lot of this research program is that there are like two modes of thinking. And there's one mode of thinking which is a little bit closer to baseline Bayesian rationality, right? And there is another mode of thinking which is sort of what looks like heuristics and biases. And I mean, the fact that there are these two modes is not something specific to quantum cognition, right? It's all over the place in psychology. It's one of the most important distinctions, that most established distinctions we have. And I suppose quantum offers a perspective for uh, what these different modes represent. And this perspective is that in one case we have um, baseline Bayesian theory, and in the other case we have like these incompatible representations. So understanding, having some sort of theoretical tools to be able to understand um, the sort of difference between the two modes raises the question that it might be possible to understand under what circumstances somebody looks more rational versus not. So I mean that has a lot of applications in behavioral economics, in the sense that if you want to say your respondents or your participants or the people you interact with to be more one way versus another, you might have some understanding of how to do this. For example, let's say that I want to, I'm kind of like a slightly unethical Gallopole designer, and I would like to design my Gallopole in such a way that have very, very strong order effects. Let's say I've got a vested interest in a particular question, and I want this question to appear as very high. Then I can take advantage of insights from this research program. For example, the fact that usually unfamiliar question combinations are more likely to be incompatible, and use that to create these order effects. In educational psychology, I suppose the equivalent would be that if you want people to reason in a certain way for a particular domain, then you can manipulate familiarity, you can manipulate pressure, you can manipulate the extent of knowledge that you're giving them. For example, sometimes less is more, sometimes giving too much information. So according to this framework, if you believe everything at face value, according to this framework, if you provide too much information, you're more likely to get participants into a mode of reasoning which is more quantum-like versus more Bayesian, right? So, but if you have more knowledge, more quantum-like reasoning, then that's more prone to fallacies. And in fact, in sort of science communication literature, there've been actual people in published research saying things like scientists might be able to serve the large population better if they provide less information. I mean, I don't believe that. I believe in transparency, but I'm just saying the idea that sometimes complexity can be bad has been recognized. Likewise, in educational psychology, let's say you're trying to teach about something, right? Sometimes too much information to start with may be counterproductive. So, but I suppose there's another side to in relation to the educational angle, and this is, well, the quantum theory and so the traditional Bayesian probabilistic inference, well, actually they have very different ways in which they're operated. In Bayesian theory, nearly in its entirety, it's algebraic. You have equations which can become complicated, and you have to deal with these equations. Quantum theory obviously has an extremely sophisticated algebraic format, and some of the most intelligent scientists of all time have created this algebraic format, but it's also got like a sort of a format based on figures. So you can go quite a long way using quantum theory with just these diagrams without doing any of the algebra. And of course, there is a pictorial format as well, which is what Bob Kirk and others and USelm have been promoting. So there's quantum theory has a format which is completely based on pictures, a completely pictorial format. And it may be the case that allowing people to have this dual format of operating the theory will unleash more creativity. What I mean by this is some people are better at using algebraic expressions. Some people are better at dealing with diagrams or pictures. And currently the a lot of the form of the science is structured in such a way that essentially we're excluding the people who may be bad at algebra but extremely good at sort of having a extremely good at dealing with geometry or geometric constraints or pictorial representations. And quantum theory allows another window for these people to actually be creative in science. So, I mean, there are, I suppose, just, I mean, sorry, it was a long answer and, it was slightly unfocused, but it was a good question and it had lots of angles. I suppose there is an angle in relation to just practical implications, how can we get into one format of thinking versus another, right? But also it's the I suppose quantum theory has this versatility, and maybe this will allow more people and more diverse people to engage with science.
Absolutely, I agree. So Irene has a question. Irene, could you unmute yourself?
Yes, thank you very much. That was really cool, very impressive. I have a question about something that you did not cover in your talk, but it's something I'm very interested in. And it's whether you have any predictions about um, whether quantum theory can be a useful tool to understand decision making, particularly in children.
Right, right. We kind of want to do some work there, but we we don't know how. But I mean, so right. So there are actually there's actually some research in relation to the way the frontal faculties of children develop or are different relative to adults, right? And it's possible that this creates this allows some predictions in terms of how many questions children are able to concurrently process or study or be familiar with relative to adults. So, but actually, there is a converse prediction as well. There's a converse possibility as well, because we think that the right there are two perspectives and they're quite confusing. So the one perspective is that children have not had they haven't got the mental capacity or the mental faculty sufficient to consider a problem in its entirety, and that means you have like these broken sets of questions. So that means more likely quantum representations, right? That's one perspective slash hypothesis. Another perspective slash hypothesis might be that because the range of questions children consider is more limited, the more likely to be able to get the familiarity across all their questions in a way that look more Bayesian. We don't know. It would be interesting. I mean, it's one of the situations where it looks a little bit like we can have our cake and eat it. That is, either way, it supports our hypothesis. But before we get to experiments, I think we need to just be a little bit more clear on what the prediction is. Can I just say, because both this question and the previous one, I mean, essentially, right, I think the major challenge in applying quantum theory more widely, that is in education or in developmental psychology or whatever, is this problem here. Let me actually just do it like this. Hold on, just give me a second. Right. So here I try to illustrate how you can have like a quantum representation where things are nice and simple, and a Bayesian representation where things are more complicated but you get more accuracy, right? Now, unfortunately, we have no idea how to go from this representation to that representation, and the problem we are faced is that with a few exceptions, so far almost entirely we just borrow tools that already exist from physics, from quantum foundations, basically. Now, there are problems that have arisen in this cognitive application of quantum theory that physicists have just not been interested in. And I suppose a lot of our effort goes into trying to get them to solve these problems for us. So if you're a physicist, the question, the problem of how to go from incompatible to compatible representations does not exist. Because things in nature, well, they're either compatible or incompatible. Velocity or momentum don't just decide to become compatible because they spend a lot of time with each other, right? Whereas in psychology, we think that is one of the key technical challenges from a quantum foundations perspective. That is how to, if you start with a representation of observables, which are basically incompatible, how to smoothly evolve this representation to something that's compatible. I kind of think, I mean, that's a guess, I could be wrong, but I kind of think that once we have some more clarity on these kind of questions, then it'll be possible to have more precise questions on issues like the one you asked about, like, for example, developmental psychology, right? Because then that will allow us to have more concrete predictions, for example, about complexity estimates. And then, we could say, well, if you have like this range of questions, then this is what we predict. Or say, if we have this exposure to question combinations, this is what we predict. But currently, we're not in that place. It's a good question, though. It's certainly something both myself and others have considered. That is the developmental implications in relation to quantum versus quantum-like. We call it quantum-like. It's not really quantum in a physics sense. And Bayesian.
Wonderful. I can't see any comments and questions in the chat box. I presume that and we are running out of our time as well. So this is a fascinating talk. I have one more question, but I will ask this in person, hopefully, when I see you.
Looking forward to it.
Thank you, everyone, for joining us for this.
Thank you for the invitation. Thanks for your attention again.
Thank you very much.
Goodbye.